Hello, and welcome to Chapter 10 of College Physics Second Edition, the OpenStax text. This is for Aquinas, Physics Without Calculus. Today we'll be going over concepts of rotational motion and angular momentum. As usual, I use the OpenStax created slideshow. I go over the base concepts. I go over specific questions from the chapter. I did not go over all of them. I highly encourage you to read along the text with me. This is not your only source of this information. Please go anywhere you can to try to find this stuff, figure this stuff out if you're having issues. Yeah. With all that being said, let's get into it. So, rotational motion, angular momentum. This should sound similar from last chapter we covered because we're going more in depth into, again, that rotational motion and how that interplays with work, with energy, and how it all comes together, centripetal, acceleration, how all these things work. Rotational motion is all around us. The class example here of the tornado shows the power that comes from the rotation. Even though tornadoes in a very small section using a relatively small amount of area to whip up its winds, they become very violent very fast, right? You have winds going up to 500 kilometers per hour. That's faster than, say, a hurricane, for example. Right? Hurricane is basically strongly blowing wind as well, but hurricanes are very large, tornadoes are very small. Tornadoes are a lot more powerful than in the individual spot than a hurricane. And allow that when we get into the math behind rotational motion and angular momentum. Hopefully you'll see what I mean by that. Whenever you watch, say, a figure skater do some sort of move on the ice, I think they're called pirouettes, I think, they always kind of follow the same trends, right? They're lifting a leg, they're spraying their arms, they're bringing their arms back in. There's more than just the beauty of figure skating involved in these precise motions that figure skaters do. There's a lot of physics and science behind how to move what in what way to achieve a said result. And again, when we go into this, you will hopefully connect some of these concepts to understand the science behind something as beautiful as figure skating. So in order to understand the math, we're going to have to go over a couple examples here. We're going to use that weird looking W. I think that's an omega. And we use V's, R's, thetas, all these things we've seen before, right? Theta, of course, is an angle. R tends to be a radius, right? You tend to see that as a radius. As an example, if we deal with circles, R is a radius, and V is some velocity. Now, V velocity, as you notice, that green arrow is not curving. The green arrow is instead going straight. So track back a couple chapters when we talked about centripetal velocity, centripetal acceleration. When your car goes around the corner, you slide across the seat to the door. Why do you slide across the seat to the door? Because you want to keep going straight, because you have some momentum inside of you. You have some inertia that you want to keep going in a straight line even though the car is curving around you. So that V, that velocity, is not curving, it's straight, because that's the inertia, that's the momentum, that's Newton's first law of motion, right? A force will continue along that force unless acted upon. So the velocity there, that's in the equation that we're showing here, is not necessarily a curving velocity, right? Your angular velocity is in fact that omega that we talked about again way back when we went over circular motion, centripetal acceleration, etc., etc. So, yep. Just to get those down real quick. Circular motion. In circular motion, linear acceleration occurs as the magnitude of the velocity changes. If your velocity is a linear velocity, again, your inertia, then your acceleration is going to likewise be linear. It kind of follows because what is acceleration is change of velocity. You can change velocity direction, but when you're going on a circle, you're not any instantaneous activity, any instantaneous snapshot of that velocity is always going to be in a straight line. That's how the inertia works, right? The tangential acceleration pulls you in towards the center. That's right. No, centripetal acceleration pulls you in towards the center. Tangential acceleration, by definition, is a tangent, so it goes perpendicular to said centripetal motion. There we go. That's the image that I was looking for. Your centripetal acceleration, we talked about a couple chapters back. That's the inward pull as you go around the corner. That's the friction of the tires to the pavement that's pulling the car in around the corner. As you, without that same friction or without that same centripetal acceleration, get thrown out over to the side of the car, and then the car door, assuming it's there, you don't go flying out of the car door then provides the centripetal acceleration to make you go around the corner. That we talked about that more extensively in previous chapters. Same thought applies. However, when we're going through these examples and you're seeing a V and you're seeing an A sub T, all those things, remember these images. That's where we're getting them from. So let's go over an example of these conversations. Again, look at the difference between that A and the alpha, right? You're probably aware of this because you're a few years into college level mathematics, right? But you're going to be reusing a lot of these Greek symbols and these Latin letters and stuff like that for various things. So in this case, alpha is going to be your rotational acceleration, and A is going to be your linear acceleration. All right, so again, we have the equations. I don't go through the book extensively. I expect you to use this as a companion piece to reading through the book. The book's going to have the equations in it. So focus in on the book. That's your primary best source of this information. All right, let's do example 10.2. A powerful motorcycle can accelerate from 0 to 30 meters per second, low of 100 kilometers per hour, in 4.2 seconds. What is the angular acceleration on its 0.32 meter radius wheels? Angular acceleration. That's not linear acceleration, it's angular acceleration. Linear acceleration is your tangential, right? It's linear, it's a line. Angular means it's curving. So angular is your alpha right here, and linear is your A. So, as I said before, we can solve these things by first figuring out what we need. We need alpha. Alpha is defined by equation 10.4 as A sub T over R. Cool. Do we know the radius? Yes, we do. It's given to us. Do we know the angular, the acceleration that's tangential, the linear acceleration? Well, we're lacking that, right? But we can solve it. Since the acceleration is the velocity divided by the time, the delta v divided by delta t, we can figure out our acceleration easily and then punch that number 7.14 meters per second squared into our rotational acceleration equation, which is that acceleration divided by the radius, to get 22.3 rads per second squared. Rad, of course, is a unit as a radian. That is a unit describing motion along a circle. And it's as with this chapter and all the chapters previous, it's about knowing what the information is giving you, determining what you know, determining what you don't know, and finding the equations that match the pieces together as best you can. So that's why I say it every time, right? Go through the book, take good track, write down your equations, write down your knowns. If you're getting lost, it's probably because you're not doing your good due diligent paperwork. Here's a nice little table relating the concepts together. And yeah, let's continue on. So as we go on to the next chapter here, we can talk about a bit of the kinematics, or your chapter 2, chapter 3 stuff, right? Velocities, accelerations, how things change over time. When you're fishing, right? The reel is what's actually pulling in and letting go of the line. And that's a rotation. That's a circle that you're spinning to produce some sort of length of fish line, or to attract some sort of length of fish line in a set amount of time. You're very much dealing with rotational energy throughout that entire conversation. Anything that rotates applies some level of kinematics, some velocity, some acceleration, some change in position to it. Just we can't use the same linear equations that we use in chapter 2, chapter 3, right? Your VF squared equals VI squared plus 2AT and all that other jazz, because things are going in circles, and that makes it all more difficult, of course. Yep, there's all the equations, and they're pretty similar rotational comparisons. A lot of these are sometimes just as easy as changing the symbol to better match what you're doing. So let's go over an example of, what's that, 10.6 I said? Yeah, 10.6. Notice here in this chapter, there is 1, 2, 3 questions before the one I get to. If this question doesn't leave you with a good enough understanding, go back and do the questions before this on your own to get a better grasp of the concept. All right, so calculating distance traveled by a fly on the edge of a microwave oven plate. A person decides to use a microwave oven to reheat some lunch. In the process, a fly accidentally flies into the microwave and lands on the outer edge of the rotating plate and remains there. Okay. If the plate has a radius of 0.15 meters and rotates about 6 RPMs, or rotations per minute, calculate the total distance traveled by the fly during said 2-minute cooking period. So, what does it ask us to solve for? What does it give us? How can we get where we need to go? So, total distance traveled. Is that a total distance traveled X, as in linear distance traveled, or is that a total distance traveled of one of the new variables that we were given? Well, if the thing's going in a circle, we need to care about rotational. We need to care about the rotation involved there, and therefore our variables are going to be the rotational variables, right? You can figure out your revolutions, or your theta, as you go around the circle, and then use an equation to relate linear distance to that rotational distance. Or, as shown here, theta equals omega t, because omega is that velocity in the rotational direction. So we can figure all that jazz out, and then we can work towards finding a solution of how far the bug actually travels. So, knowing said information, we know the angular velocity, because that is how fast the plate's going in a circle, and it takes about 6 rotations per minute. So if you're rotating 6 times a minute and you cook for 2 minutes, and you have 12 total rotations, right? Or revolutions around the circle. And then we can use that equation. We can calculate that out into rads, as shown here. Every revolution, every circling of the plate is 2 pi rads. So we hit 75.4 rads. We go around the circle. And then keep in mind that 75.4 rads, as shown way up here in this nice table here, so 75.4 rads gives us a distance based on the time it takes to do it. Sorry, it gives a distance based on the size of the plate. Sorry, my apologies. So if we're going 75.4 rads and the plate itself is 1.5 meters, then you're traveling essentially 11 meters distance in those 12 rotations. The equations themselves, once you know how to click them all together, are pretty easy solutions, right? That's a pretty short amount of work needed. But you need to realize that theta for these equations does in radians, and we're given rotations per minute, so you got to transfer it over, right? You got to connect these dots that are not explicitly given to you to solve the problems. The next conversation is, rotational energy and rotational inertia. When things are circular, right? I can't really adequately apply a force in a circular motion. This example here, right? Pulling the tire. You apply a force more or less linearly, and then or snapshots linearly, and then the result of your force is some sort of acceleration rotationally. But that being said, the two are very much interconnected, and you can easily transfer linear force into rotational inertia or rotational energy, rotational momentum, all those things, right? These are all conversations we've been having. These are all equations we've touched on. So, the lots of tabletop games and stuff like that, dexterity games, revolve around this idea of applying a force and watching a circular motion happen and a circular motion result from it. And one of the things that always tricks students up is the rotational inertia, or how the thing moves and the way it moves is very spatially dependent, is very dependent on the shape of whatever's moving. Here we have, I think the book actually has a zoomed in version of this. Let me check. It's a bit more zoomed in, yeah. The book here shows you that the inertia, the energy involved in something when it rotates, is highly dependent on what it is and how it's rotating and what the shape is. Notice here at the very top two, for example, are we dealing with a hoop or are we dealing with a ring? Because if we're dealing with a ring with some set thickness, then you have all the mass incorporated in that ring, applying gravitational energy, applying centripetal force, applying motion to continue the revolutions. Those four axes, those four like straw looking ones in the center there, are very interesting because you have the same object, but you're spinning it differently, right? That can, of course, can net you very different results depending on what axis you're spinning it around. And lastly, we go down here, blocks behave differently, balls behave differently. When you're given a question, you can't just, if they tell you some interesting information that may play a factor in what equation you just solve for, this is a frame of reference point, essentially, right? The fact that the plate was a plate didn't matter because I cared about the fly. But if I was asking questions about the plate in some way, I was applying energy like to the plate, then I may have to care about the shape of it to solve my problem. So let's go over this conversation and let's take a look at example 10.7, a merry-go-round. When you apply forces a merry-go-round, what does it actually mean? So consider a father pushing a playground merry-go-round, as shown, guy in the green shirt. He exerts a force of 250 newtons at the edge of this 50-kilogram merry-go-round that has about a radius of 1.5 meters. Calculate the angular acceleration. So again, go back to your knowns, what letter, Greek letter or Latin letter happens to be angular acceleration. Calculate the angular acceleration, A, when no one is on the merry-go-round, and B, when an 18-kilogram child sits 1.25 meters away from the center. We're going to consider the merry-go-round essentially a uniform disc, where those handlebars don't matter, and we're gonna not care about friction. Why? Because it just makes our lives easier. So we got to go and we got to consider what we're talking about here. Angular acceleration is given directly by a known expression, the tau divided by I being the inertia, tau being the torque. Two things we've already talked about in previous chapters. We're bringing those together again here, right? To solve for said acceleration, we need to calculate the torque, which is not given to us. But the same in both cases, because the torque, what's given to us, because we know the force applied, right? But the force being applied is the same, and the inertia is different. Why is the inertia different? Because the kid sitting on there adds additional mass, at a non-centered at a specific spot on the shape, on the geometric object. So our inertia is affected in that way. Torque, again, I think from a previous chapter or two, is given by the radius times the force times the angle which you're applying said force. A force is basically perpendicular, so the theta comes out to 1, which means it's our rotation, it's our radius times our force to give us 375 Newton meters of torque being applied to the system. And now we need to stop and think, okay, what is spinning? Well, essentially a solid disk is spinning, right? So how does that affect the inertia of the object? Well, a solid disk is given to us by the equation. Where's the equation? 1/2 mr squared. M, of course, being the mass, R being the radius. Yeah, figure 10.11. There we go. Where's it at? Oh, it's this guy here, right? 1/2 mr squared, because R1 and R2 are equal, so it's a solid disk. It says they butt up to each other, so you don't need to like add the halves. We can figure out the inertia of the blanked out merry-go-round by calculating it out. So 1/2 times 50 times 1.5 squared gives us about 56.25 kilogram meters squared of inertia. And then our initial equation that we talked about at the top here, divide out to give us angular acceleration 6.67 rads per second squared. Cool, easy, no real problem. But what happens when we add the kid? Well, we would expect the angular acceleration system to be less because the moment of inertia is greater in the child in the merry-go-round. It takes more force to move with the kid there. And the placement of the kid has a big impact, right? The closer the kid is to the center, the easier it is to spin. Further outside, harder it is to spin. Thus, to find the total momentum of the inertia, I, we must first find the child's momentum, I sub c, considering the location and mass of the child. So we could figure out the child's inertia by essentially making a disk at that distance. We have the child itself moving, 18 kilogram child at 1.25 meters per second. The child, not the child on the disk, just the child moving. The system is just child here. The child itself is 28.13 kilogram meters per second squared. So when we add that child to the disk, we get a larger total inertia. And again, that's the weird part, is we're separating the systems out because each one is kind of independent for this conversation. And then once we know the child and we know the disk, we can just sum them together to find the child disk system inertia. Once we have that, we plug in our new numbers and we get, as expected, a smaller acceleration, 4.44 rads per second squared. Meaning, again, this is another one of the examples of you know it intuitively, and the math also verifies it. Once you sit the kid on there, you got to put more force in to achieve the same acceleration. Increase the mass, increase the force, right? F equals ma. All this stuff goes back to our very simple equations. Well, simple to a certain extent, right? This stuff is getting complicated. Kinetic energy, cool. Let's go to the next chapter here. Kinetic energy is the same conversation we've been having a while, right? Kinetic energy 1/2 mv squared. You rotate that energy, you still have that kinetic energy still exists. Just we care about different variables in the equation that kind of have different symbols for them, right? Net force is still being defined, as we said before. But the work done, instead of a linear distance, now we have an angular distance. We have a curving distance. So instead of like a delta x, we have a delta s, which is the outside edge, how far the thing travels around the corner. That's what we care about for our rotational kinetic energy, because things are spinning. So we care about the fact that things spin. You can You can be on a flywheel on a bus. This is more of the same. I'm going to skip over this particular section here. I think you kind of get in the conversation. This particular question, again, sorry, this particular symbol comes from a question. Sorry, my kid came up and interrupted the lecture. What I was saying was this particular, I thought about doing this one or the next one, and I chose helicopter as an example, but this question, which is, which one is it? Here it is, 10.8, very good example of the conversation we're talking about. If 10.9 doesn't click with you, come back 10.8 and discuss it. I'm gonna keep saying that because I want you guys to go through this stuff on your own if it's not clicking with you. So that being said, let's go over 10.9, a rotational energy question involving a helicopter. How fun. All right, so a typical small rescue helicopter, similar to pictured here, has 4 blades. Okay, each blade is 4 meters long and has a mass of 50 kilograms. The blades can be approximated as thin rods that rotate about one end of an axis perpendicular to their length. So they're spinning, right? We're basically saying we're going to skip the dimensions of the blade for sake of simplicity. The helicopter has a total loaded mass of 1,000 kilograms. Given this information, can you calculate the rotational kinetic energy in the blades as they rotate some 300 rotations per minute? And then calculate the transitional kinetic energy of the helicopter when it flies 20 meters per second and compare that to the rotational energy of the blades. Lastly, to what height could a helicopter be raised if all the rotational kinetic energy could be used to lift it? So a lot of stuff there, but if we consider our equations and our variables, again, the equations are shown above here, right? So you got to go through the book to find the equations to solve these problems. So considering the rotational and transitional kinetic energies in the equations provided, what do you do? Well, first of all, write down your equations, figure out what you know, solve the problem, right? Rotational kinetic energy, or KE ROT, is equal to 1/2 I omega squared. If that's not omega, someone please tell me. I want to say that's omega. Do we know these things? Well, yeah, we do know that angular velocity because we know how fast it's revolving and we know for how long it revolved, right? So 300 RPMs is 300 rotations per minute or revolutions per minute. So that's easily translated into 300 over 1. There's some good, what do they call it? Dot bar math, I think is what's commonly referred to as, right? Unit conversions. So 300 RPMs is 300 revolutions per 1 minute. And then we know that there's 2 pi radians in every revolution. And we know that there is one for every 1 minute of 60 seconds. So we can convert 300 RPMs to 31.4 rads per second because rads per second is the angular velocity variable that we care about to get our joules at the end. Inertia, likewise, found by following the formula. We know the inertia of each thin rod because we can look at our graphic to refresh your memory. This guy here, we can find thin rod rotating around the end of its axis. That would be this 6th one down here. That equation is mass times length squared divided by 3, and then we have 4 of those, so you multiply that number by 4 to get the total inertia of the entire object. And then our rotational kinetic energy is just 1/2 times our I times our angular velocity squared, 1/2 mv squared in this case. It's 1/2 I omega squared, and we land at a total kinetic energy of 5.26 times 10 to the 5th joules. Cool. Find the equation that has what you need to solve and solve it, right? Translational kinetic energy is also given by the linear kinetic energy. Translational, linear, same thing, right? When we're talking angular, we tend to say translational because it reminds you of the perpendicular nature that the energy travels, the direction it travels any particular snapshot, right? So 1/2 mv squared, that's given directly by the helicopter. The helicopter has subset mass, it's moving at some said velocity, so we have some said translational energy. Comparing these ratios, we get a 0.38 or 38% of the energy created by the blades is going towards that motion. So what is the maximum height that this thing can reach? Well, what does that maximum rotational energy give you? And remember, kinetic energy and potential energy are directly linked. So that how much kinetic energy gets you how high? Or solve for the H, right? Again, something that's not explicitly stated, but if you remember that potential energy has a height indicator, and gravitational potential particularly, I should say, has a height given gravity, you can relate these numbers back together and find out that purely the helicopter's blades, just the helicopter's blades, are giving you 53.7 meters of height given that rotational speed. So yeah, it's all about knowing your equations and solving them out. This is also a pretty good question that I'm skipping over at this point because I want a different one, but it's referring to conservation of momentum and kind of how the size and the heaviness of an object will affect how fast it rolls. A empty pop can rolls slower down a ramp than a full pop can. Why? Because the full pop can has that additional mass, and that's adding to the angular speed at which it gravity imparts on it. And again, this is a PE and a KE conversation. Yep. So momentum, same song and dance with the energy. Momentum is conserved the same way energy is conserved, but momentum is how fast you're going and how heavy you are. So we can again consider torques and various things like that to get out interesting answers. Equations are given to you in the text. Make sure to read through the text carefully when you're going through and answering these questions. If you don't know where the equation comes from, go back to the chapter and try to solve it out. The questions at the back of the books that I give you are organized more or less by chapter, right? When you look at them, you see what chapter the questions come from, so you can go there to solve your problem. Let's discuss 10.13. I picked a medical example because I know some of you students plan on going into medicine, so you're welcome. The person whose leg is shown in the figure below kicks his leg by exerting 2,000 newtons of force with his upper leg muscle. Now, the red thing up there by the femur. The effective perpendicular lever arm is 2.2 centimeters, so that's the lever that's doing that rotation. Given the momentum of inertia on the lower leg is 1.25 kilogram meters squared, so I'm giving you I of the lower leg, find the angular acceleration of the leg given that force, and then let's neglect gravity to determine the rotational kinetic energy of the leg after it's rotated some 57.3 degrees, so about a rad of distance. So how can I solve these problems? Well, I'm given I, the momentum of inertia. I know that the acceleration is given by our force times our force and our mass. In this case, our force is some torquing applying that the muscles applying to the leg, and our mass is essentially given by the inertia of the object, which is known. So we can solve that acceleration based on those two factors there. So our tau, our torque, right, is again the force being derived over some rotation. That's how torque works. We talked about that a couple of chapters ago. And we know the rotation, the distance that the object is rotating, the force being applied to it. So our net torque is some 44 Newton meters. Dividing that out of 1.25, the inertia, kilogram meter squared, lands us at a total acceleration of 35.2 rads per second squared. Cool. Pretty interesting, right? That's how much that big muscle torquing that little teeny connecting part gives our leg pretty decent amount of acceleration. So the second part was the rotational kinetic energy after X number of rotations. So as it's rotating up, how much kinetic energy you have as it straightens out, essentially. So this is a kinematic conversation because we're having the leg is traveling. Traveling is kinematics. We had 2D kinematics way back in chapter 2. Now we have rotational kinematics from a couple, 10.3, I think, had rotational kinematics. Expressly, we have 10.104 and 10.105 here explaining the conversation. But we don't have to necessarily go to those kinematics because we can remember our kinetic energy equations too, because there's set number of motion. We know how fast the thing's moving, so we can also figure out how fast it's moved after a certain amount of time. We know how much energy is being put into it, right? So rotational kinetic energy can help us quite a bit in solving this problem. The most convenient use of this is found by plugging in said rotational acceleration into our equation here to find our rotational velocity. Once we know our rotational velocity, kinetic energy is directly related to the velocity at some said moment, and the math solves itself. Kinetic energy is energy of something moving. I tell you the leg is moving, you should maybe check out kinetic energy. Kinetic energy requires velocities by giving you acceleration. You can relate velocity and acceleration very easily, right? All these equations play together. If you're getting lost, have your equations written out and know what the variables mean. Now we can finally get back down to the initial example, that being the figure skater, right? We've talked a lot about kinetic energy. We've talked about transfer of momentum. All these things play in a figure skater's motions and what they do to achieve the result. Why do they bring their arms in? Well, they bring their arms in because you're changing the center of gravity. Again, another thing we talked about before. You're changing, well, you're not changing your center of gravity, sorry. You're changing the length at which the rotation is happening. When you bring it in, right, you are adding angular momentum by conserving the total force and changing the distances involved. It is fascinating that you can math this stuff out and find out that it's correct, right? I don't know, I think that stuff's kind of cool. And this goes for figure skaters and it goes for entire solar systems, right? Part of the way we can figure out how old a solar system is, or if anything tragic has happened to it, is by calculating and recording the total angular momentum of what's moving around. If these numbers are greater or lesser than, it tells us something about the history of entire bodies of space. That's pretty cool, right? Yeah. So bowling pins, another example of these things affecting each other, and everyone's very happy to know that. Right, let's go through an example in the text and discuss this conversation. So this example here refers to collisions. So again, this is something we discussed a chapter or two ago, and we're just slapping that paint of rotation and circles on things. A lot of our equations are going to look very similar, right? But we just have to remember that we're dealing with going on a circle. So you don't have A, you have alpha, right? You don't have V, you have omega, stuff like that. So image here, right? Suppose you have some disc and you're flicking a disc at a nail that's nailed into a stick that's been nailed to the ground, so the stick can go around like a clock hand, right? The disc that you flick has a mass of 50 kilograms. You flick it at 30 meters per second. Wow, that's a flick, right? It strikes a 2 kilogram stick that's about 1.2 meters long. After this happens, right, conservation of energy, conservation of momentum, keep all that in mind. What is the resultant velocity of each components, the disk and the stick, how much kinetic energy exists, and what's our linear momentum of the conversation. So what do we know? What can we solve? Well, we know momentum is conserved, therefore we know angular momentum is conserved. So if we can figure out the initial momentum, we know our final momentum, and then we can break that down into the individual parts and see what holds where. So momentum, again, given by, in I think 10.5, momentum is given by our inertia times our angular velocity, right? Very similar to momentum in a linear setting here. So we can know the moment of inertia and the angular velocity around some pivot point, and keep in mind what we're dealing with here. For example, the disk, we're going to say has initial a moment of inertia of mr squared, because we're essentially considering it a mass, right? The disk shape is not relevant to the action that's happening. What is the system here? Is the disk doing something internally to itself? No. So we consider a point mass, so we can use the simple inertial equation. Of course, angular velocity is v over r, so we can retranslate our initial equation into something that has the variables we care about, right? I'm not given angular variables, so I need to rewrite my equations to not have angular variables in them. After collision, same conversation. So we can write out our equations to these primes here representing before and after, right? Before is right here, and after, of course, would be right here. So given all of that, let's solve out what we have here. So that I prime is on a moment of inertia after collision, okay? There's more inertia of the stick and the disk as they're stuck together, which is the sum of the individual moments of inertia around the nail, as said before. We can use our equation and what we've had here to summarize up a big equation describing, again, that rod as it spins around. That's one moment of inertia equation, and the disk, a different moment of inertia equation. So that's what we're looking at here at equation 128. Plug in our information, and we solve it out pretty readily here. The moment of inertia of the stick moving around here is given by the mass of the object's second object divided by 3 over r squared, give us some said number. Excuse me. Plugging that into our original calculated equation gives us an angular acceleration of the total object here. Cool. That people always try to trick you in this stuff. Before and after energy, always the same, right? As things are moving, things are moving. The kinetic energy before the collision and after the collision is the rotational energy of the two. So there you go. Before the collision, you can calculate out how fast the puck was moving. After the collision, you know the rotation of the stick. So solve it out. You get yourself about 1.57 joules in the stick as it's moving around. Lastly, it was what, momentum, I think? Yeah, total linear momentum before and after said collision. Linear momentum is before the collision is just the disk. After it's the momentum of the two. We can figure out the initial momentum because we know the heaviness and the velocity, and our final momentum has to account for all of that. So again, we are summing the stick and the momentum of the stick and the momentum of the disk together, noticing that things are rotating, so we're caring about slightly different variables here, right? It's not doing a velocity, we're doing rotation times our a radius times our rotational velocity. Plug in all those numbers in, we land at a useful, and the momentum there, 2.2 kilograms per second squared. So do all this stuff, and this question, I guess I maybe should read it better. Did not do a good job of explaining the inelasticity of the equation. The picture like does that, and I mean it says it, but not very well, right? So that was something I should have explained better at the beginning. I apologize. But you do note that our initial and final kinetic energies and our initial and final momentums are a bit different. Well, why? Because you're doing an inelastic collision here. So you're using up some of your energy in that sticking together of the thing. Why do you have more momentum? Well, because you're dealing with the momentum and it's rotating around the sphere. So you got to take all those things into account. Yeah, there you go. That's collisions. Takeaway from this example, first of all, read better, realize it's inelastic. That'll help you out a bit. Secondly, we're still in that process of what do I need to know? Do my variables match? As something's rotating, I need to care about rotational variables. Something's going straight, I need to care about going straight variables, but they all interact with each other. You're talking about the same things, just sometimes you got to throw a radius or a sign in there to make everything add up out. Right. Again, this is a good example. We have mr squared is the disk of the moment of inertia afterwards, and we're adding that to mr squared over 3, which is the stick rotating around a point axis at its end. Right. Cool. A lot of the stuff is kind of still the same thing. Rotation and where you apply forces, where you apply torques. Cool. Right-hand rule for disks. When we get into electricity, we'll care more about this stuff because there's a lot of interesting synchronicity between various seemingly different parts of physics. But we're not going to go into that too much. This has to do with gyroscopes, actually, I believe. Yep, it has to do with gyroscopes. And essentially, rotation. I don't think I have you do a math for this, do I? No. Okay. When you apply rotational force, there's force, yeah, going in that tangential direction to the outer ring of the rotation, but you also apply, funny enough, a force perpendicular to the entire object. What that red arrow is representing is actually a force going up and down outside of the spinning, whatever's been spinning. In high school physics, your teacher probably did the bicycle wheel example, right? Where you get a bicycle wheel spinning, and then when you try to like spinning perpendicular to you and you're standing on a rotating platform, and then when you turn the bicycle wheel so it's parallel to the ground, you'll spin on the platform. And that's because the bicycle wheel is imparting rotation gyroscopically through its center, and then it's spinning you. Lots of cool stuff with that. It's kind of how gyroscopes work, right? That's how they keep standing. Tops and stuff like that do this exact same conversation. It's why you don't have to worry about balancing when you're on a bicycle. Very fun stuff. Again, a lot of these last chapters don't go into new math, instead they go into an application. Gyroscopes are an application of this rotational energy. So there you go. That's chapter 10. I a bit flubbed on this example because I forgot to say it was inelastic at the very beginning. Picture the table job of it reminding me of that. But yeah, more of the same that we've been going over. Find your equation, find your knowns, solve out what you don't have for. The more you write this stuff down, a lot of you have been doing very good jobs at your homework of noting what needs to be noted. It's amazing how much how fluid some homework is when you take proper notes and write things down. So take your time and do that. And yeah, thanks for watching.